organize the reactions differently. But we are looking at chemical reactions, i.e. chemical properties. And so what we want to do is we want to understand the properties of matter by looking at the structure and the composition of it. So, let's see. A little editing. Chapter 8. Chemical properties. When you think of physical properties, you can think of a lot of physical properties that might come to mind, like boiling point, freezing point, density. But when you think of chemical properties, what types of things come to mind? Combustion, that's a good one. Fermentation, yeah, those are good. Like, so for example, if somebody asks you, what are the chemical properties of water? What would you think? Is water combustible? No. Doesn't burn. It's pretty stable. Can you think of any others? Chemical properties of water? We can think of physical properties of water. It's pretty simple, like boiling point, 100 degrees. Freezing, 0 degrees.
What is distillation?
Distillation is physical property. It's a physical separation technique. Distillation is used to purify water. And so, how about a chemical property of water? Can you think of any? Solubility would be physical property, yeah. So we have to start thinking in terms of chemical properties. Is that it? Just combustion, fermentation, that kind of stuff? Or is there more or less? And so what we're going to do is we're going to look at 3 categories of chemical properties. Combustion would be a category called a redox, but we're going to divide that. We'll look at redox kind of at the end. So when I think about chemical properties, I think of these 3 things. One, does it undergo any metathesis reactions?
Is that with metals?
Metathesis isn't referring to metals. Metathesis is referring to switching partners. It's like metamorphizing.
Does that say reactions at the end?
Yeah, it says reactions at the end there. Metathesis, metathesis. Then I look at acid-base reactions. We'll talk about acids and bases next. And then we look at what are called oxidation-reduction reactions, or redox reactions for short. So let me write that there. Combustion is an oxidation reduction reaction. Or redox. So these are the types of reactions that we look at. So if somebody asks you what are the chemical properties of water, you'd think, are there any metathesis? Are there any acid base? Are there any oxidation reduction? And that pretty much covers it. You know, these are the 3 main types of reaction. And then we have like variations of these as well. So normally when we think about chemical reactions, there's a lot of different chemical reactions. So there are the, here are the learning objectives for the class. So one thing is, how do you recognize a chemical reaction has occurred? You recognize a chemical reaction has occurred by change of color, but change of color could also be a physical, like dilution. You know, sometimes things become lighter or darker if you dilute it or concentrate it. But if there's a significant change in color, then that could be. It might be physical, it might be chemical, but do that. Formation of a solid product. This is called precipitation. And precipitation results from favorable ion combinations. And so we should say formation of a solid product. It's an insoluble solid product. And so we looked at the solubility rules. There's certain ions that like each other. So for example, if you have silver ions and chloride ions, they like each other. And what they do is they form silver chloride, which is an insoluble product. And so this is an example of a precipitation reaction here. And we know that chlorides, bromides, and iodides are all soluble except when paired with one thing you might want to do is, you might try doing this. You might try to review the notes. Just like read through your notes the day of the lecture. Silver, lead, and mercury. And the reason is just to develop familiarity. You know, the more familiar you become, the easier it is to study for tests. So you'll draw up fewer blanks. You know, if you go onto a test and you come up with a total blank for a particular problem, you know, sometimes either you don't have it in your neurons memory, or it takes time to dig it up. You know. And so I highly recommend this, especially, you know, if you're drawing up blanks on the last test, you want to do something to change, you know. Maybe how you approach studying would be good. And so these solubility rules, it's just like anything else. It's kind of a lot. It's kind of overwhelming at first, the solubility rules, but if you read the solubility rules like every day, like once a day or maybe even twice a day, you just read them, you know, then it's pretty easy to memorize. You don't have to do much work to memorize those. What's the point of memorizing? The point of memorizing it is it's actually pretty useful to know the solubility rules to predict chemical reactions. We use them to predict chemical reactions. So this is called a precipitate. Silver chloride is a precipitate. And this process is called precipitation. The type of reaction here is, this is a metathesis reaction. And metathesis, another way of understanding metathesis reactions, metathesis are favorable ion combinations. So silver and chloride like each other, strong enough that it forms a stable solid, a stable lattice. It's hard to break apart this lattice once it forms. That's why it's insoluble. We talked about that yesterday. Formation of a gas product. This is called effervescence. Or gas evolution. When we form a gas product, it's kind of like this. We're precipitating a gas, essentially. And so, precipitating a gas. There are some dangerous ones, like, for example, cyanide. If I had cyanide, these are aqueous, AQ. If I have cyanide in solution, for example, sodium cyanide or something, and I have H plus as well, that forms HCN. Hydrocyanic, we call it HCNAQ, hydrocyanic acid. Where does the origin of the name hydrocyanic come from?
Hydrogen and cyanide.
Well, the acid name. How do, for example, if I see the hydro in an acid, what does that mean automatically?
It's an eye.
It's an ide, good. Oh. It's an ide. And so this is cyanide. We know it's going to make a hydro. Or the hydrocyanic acid can come out because hydrogen cyanide in pure form is a gas. We don't call this hydrocyanic acid. We call this hydrogen cyanide gas. This is also a metathesis reaction. Do you see? Because hydrogen ions and cyanide ions like each other. And they'll combine to form, they don't form a precipitate because it's HCN an ionic, or would you consider it molecular? We would consider it molecular because it's made up of nonmetals. And so in molecular compounds, the bonding is a little bit different. It's not like packing together balls. If you have marbles, that's an ionic. So if you have a positive marble and negative marbles, the negative marbles will be attracted to the positive marbles. But in this case, the bonding's a bit different. And it results in a molecule of hydrogen cyanide. When you take hydrogen cyanide and dissolve it in water, we form hydrocyanic acid. And so we typically use the acid name in aqueous, and then we use the ionic name, for example, when it's pure, like this, as a gas, for acids. We can also detect heat. Heat, there are two terms for if heat is released or if heat is absorbed. Do you guys remember those two? Oh, good. Good. Endothermic and exothermic. Endothermic refers to which one?
Getting heat or like
Absorbing or releasing heat?
absorbing?
Absorbing. And exothermic refers to releasing heat. And so we just try to detect it, if there's heat being released or heat being absorbed. Emission of light, if it starts to glow, then we can see that something's happening.
Where it says formation of the gas product, what's the word you wrote after?
Effervescence.
Effervescence.
Rather than emitting heat energy, we can emit light energy as well. Heat is associated with vibrations, kinetic energy. So we look for those types of things. Here's a color change. It goes from colorless to pink. The pink color begins to fade with time. Eventually the pink color will disappear, given enough time, but there's some evidence of chemical change.
That's seconds or minutes?
Seconds. You're going to see this particular one. This is called phenolphthalein. Phenolphthalein is used to detect bases. We talked about like sodium hydroxide. Phenolphthalein, if you mix it with sodium hydroxide, it turns pink like this. Detect that. This is a precipitation. These are tiny crystals of tiny crystals of solid precipitate. I don't know what they're mixing here, but do you see it's a wispy, cloudy precipitate. Eventually those tiny crystals will sink to the bottom. Sometimes the crystals are so tiny that it takes time for them to settle. And we just wait until eventually they'll settle, but here there's clear evidence that there's some solid that's forming here because we get this cloud precipitate. This is effervescence or gas formation here. Clearly a chemical change has occurred. This is heat and light being emitted. That looks like they put powdered iron in here into the Bunsen burner. Here are these glow sticks. These are emitting light from chemical reaction that occurs. Cold pack. Cold pack is endo or exo? It's endo. This is absorbing energy from outside. Whereas a hot pack would be exothermic. Here are a number of changes. This is sodium metal. Sodium and water are not a good mixture. Sodium, one of the properties of water is it reacts with sodium metal. And this is called a redox reaction. And it reacts quite violently. What's generated here is there's some steam being generated. It's like, also there might be some oil that they coated the sodium with. They put some phenolphthalein in the water. Phenolphthalein is a dye that reacts with sodium hydroxide or hydroxides in general. And so in this chemical reaction, the water gets hydrolyzed, we say, but it doesn't form hydrogen and oxygen, it forms hydroxide. And hydrogen gas, the hydrogen gas gets evolved out here. If it gets hot enough, the hydrogen gas can ignite without an ignition source. It just spontaneously ignites. It's quite a violent reaction. Let me show. The alkali metals. What's wrong with this?
Better allergy relief for better boyfriending. Live Claritin Clear.
This one.
This is a demonstration video showing some of the chemical characteristics of sodium. When the sodium metal is
Right here, you don't want to handle sodium metal with your fingers, because your fingers contain moisture, they contain water, and so they'll start to react with the sodium metal, since water reacts with sodium metal. And so this person's handling it with a glove. Now this metal is very soft. You can cut it with a butter knife. it has a fairly low melting point. The melting point of sodium is only about 100 degrees Celsius. So let's see if they have the more dramatic. I thought they had the more dramatic one here.
As promised, we're going to experiment
This is a pretty big piece of sodium metal there. Probably about 500 grams worth.
with the larger blocks of sodium.
I wouldn't have put it in natural water because this is not good for the natural water here. But some people did this. When I was at UCSB, somebody took 500 grams of potassium metal and threw it in the swimming pool there. Which is okay because the swimming pool, the pH has to be adjusted anyway. But this is, the product of this is, well,
Metal. And to do this experiment, we ventured outside rather than to conduct this experiment within the workshop. We set the cameras up and chucked a rather large block of sodium metal into a lake of water, and after a few moments,
the 500 grams of potassium resulted in this thing that went, a plume of water that went up about 30 or 40 feet up in the air. It was pretty loud in this big flash.
Would any fish in there have like died?
Yeah. Well, the sodium hydroxide is like drain cleaner. The fish survive in drain cleaner? Obviously, it's gonna diffuse out and dilute, but one of the products of sodium in water is sodium hydroxide. Sodium hydroxide is very bad for your eyes. And so, here's the reaction between sodium and water. So we have sodium and water. It makes hydrogen gas and sodium hydroxide in heat. The heat, if it's hot enough, it can ignite the hydrogen. You don't need a spark. You don't need a flame. You just need a little bit of heat. There's a certain temperature at which hydrogen will ignite spontaneously. And it ignites because there's oxygen around. And so we have another redox. This is an example of a redox or oxidation reduction reaction here. And then we have another one with hydrogen. This equation is not balanced. So one of the things we do is we try to balance this particular equation. And when we balance it, we have one sodium, two hydrogens, and we have three hydrogens over here. And then one oxygen, we have one oxygen here. So the hydrogens are not quite balanced. So what we do is we need to make this match. So either I need three hydrogens here, or I need three hydrogens here, or I need to come up with some multiple of that. Probably one of the easiest ways to do this is we can do this. We can't have half a molecule of hydrogen, but we could have something called a half a mole. And so the way we do chemical reactions is we can use fractions to balance this, because this would be two sodium atoms. This would be two molecules of water. This would be one molecule of hydrogen, and this would be two formula units of sodium hydroxide. Now, we could do this, we could do it by atom and molecules, that is individual particles, or we could do it by dozen. So we could just say this is 2 dozen. If I had 2 dozen sodiums, then I would need 2 dozen waters, and I'd form 1 dozen hydrogens and 2 dozen formula units over here. Or I could do by moles. Dozen's too small, atoms are too small, so I could do 2 moles of sodium. 2 moles of sodium, we can see how much that is. It's a lot. And I could do 2 moles of water. 2 moles of water would be, this would be about 46 grams. This would be about 36 grams. And then I could do 2 moles of hydrogen. 2 moles of hydrogen is only about 4 grams worth. And then 2 moles of sodium hydroxide, which is about 80 grams worth of sodium hydroxide. And so I could do it in different quantities. So if I'm looking at it in individual particulate level, I can't have half a molecule. But if I'm looking at it on a mole basis, then I can have half a molecule. And so all I do for balancing this is I have 2 hydrogens here, and I could adjust the amount of hydrogen I have here to any amount I want. So I already have 1 hydrogen here. So 1 plus 1/2 times 2 gives me 2. So that gives me 2. If I don't want this fraction, then I double everything. If I double everything, that gives me 2, 2, 1, 2. And so that's what they end up down here, 2, 2, 1, 2. So the strategy I use for balancing is you save the single element for last, that is hydrogen. If I try to save one of these others for last, that screws up the balance. For example, this one, if I change it, it screws up 3 elements, sodium, oxygen, and hydrogen. If I change this one, it screws up 2 elements, hydrogen and oxygen. This one's okay, I could save this one for last, because that's only going to impact the sodium. And so that's a strategy for balancing. Then we have these states, solid, liquid, gas, and aqueous. There's also plasma state, but plasma state's not one that we encounter much. Although the plasma state in the universe is like the most common state. Do's and don'ts of balancing. We change the coefficients, we don't change the subscript. If you change the subscript to balance things, then it really screws things up. So for example here, another way I could have balanced this previous one is rather than multiply it by 1/2 here, what if I did this? Instead of multiplying that by 1/2, let's get rid of this subscript and just make this H1. Does that work? No, we can't do that because we didn't form atomic hydrogen, we formed diatomic or molecular hydrogen in this particular reaction, so we can't do that. So the do's is just change the coefficient, never change the subscript. Like for example here, maybe I can just get rid of that hydrogen and then it'll all balance out, but is that still sodium hydroxide? No. Don't add imaginary species. So, for example, here I have 3 hydrogens. Let's try to change this to 3. No, we don't do that, right? Or let's try to add an H. We don't do that either. So balancing can be a bit of a pain. Okay, let's go through and balance this one. And there are multiple approaches that you can take in balancing these. So for example, I would look, let's say, which one do you want to balance first? The phosphorus, the chlorine, the hydrogen, or the oxygen? All right, let's balance out the phosphorus. So I see I have 1 phosphorus, I have 1 phosphorus here, so it's balanced. Okay, but that if I leave the phosphorus fixed here, 1, then that's going to require the chlorine to be, how many chlorines do I have here? 5. And so I'm going to change the coefficient here to 5, so that gives me 5 HCl's. They took a different approach. That's fine. There are multiple approaches you can take. All right, so that's going to fix the H's here and the H's here. I don't want to change that, so I have 3 H's plus 5 H's is going to give me 8 H's here. So I need to do this by 4. So that'll give me 8 H's. And hopefully we'll cross our fingers and hope that the oxygen's balanced. So we got 4 oxygens here, 4 oxygens there. Now coefficient of 1 we don't write. And so they wrote the 1, but we never write 1. We just leave it blank there, and that automatically means 1. So they deleted the 1. So at the a particulate level, this is 2 molecules of hydrogen, 1 molecule of oxygen makes 2 molecules of water, gaseous in this case. But we could also do this at the molar level. And so this one gives us ratios. These are called stoichiometric ratios. What does stoichiometry refer to again? Stoichiometry is what? Yeah, it involves moles, but what is it, stoichiometry?
Like the measurement of elements.
Yeah, but what did I call it? Does anybody recall what I called it yesterday or day before? Moles, mass, measurement, yeah, that's all correct. Stoichiometry means, the word stoichiometry means, it's a funny word, or how it's defined.
Like stoic is supposed to be like element.
It's not element, it could be anything. It doesn't have to be element, the way it's used. That's all right.
It means measuring elements.
It's not just the process of measuring. You take a beaker of water, you weigh it on the balance. Is that stoichiometry? It's, or you measure the length of a piece of paper. Is that stoichiometry? No.
Does it mean to like measure them at the molecular level?
How do we measure at the molecular level? We only have one thing that kind of measures at the molecular level. What would that be? The instrument that we use to measure the molecular level. We can measure like things at the molecular or the atomic level using a well, we can measure, meaning experimentally measure things at the molecular or the atomic level using what? Like the weight, the mass spectrometer. So does stoichiometry mean we use a mass spectrometer to measure things at the atomic or the molecular level? Not really. Quantity relationships, yeah. What we want to do is we want to relate quantities of one thing to quantities of another. And so these are called stoichiometric ratios. So if I want to relate how many molecules of hydrogen to how many molecules of oxygen, I can come up with a stoichiometric ratio like this. And that is, for every molecule of hydrogen, I have a molecule of oxygen. Or for every 2, actually, not 1. For every 2 molecules of hydrogen, I have 1 molecule of oxygen. So that gives me this stoichiometric ratio here. It's trying to relate these two things, these two quantities. Or I could flip it over. I can say that there's 1 molecule of oxygen for every molecule of hydrogen. And so we try to relate 2 things or more together, and with stoichiometry, since they're quantity relationships. And so I could do it at the particulate level. This is the particulate, or I could do it at the macroscopic level. At the macroscopic level, then we want to use moles worth. That way we can bring it into quantities that are significant, that we can actually see, etc. And so this is what this side, this is saying here. And so it's a lot of wording for that. This is at the particulate level here. This is a reaction between hydrogen and oxygen. Hydrogen, one of the chemical properties is it's combustible. And we can burn it in oxygen. When you burn hydrogen and oxygen, it forms water. Can you burn water further? Or is it kind of maxed out? It's maxed out. Hydrogen has how many electrons? One. And if it loses one electron, does it have any more electrons to lose? No. It's maxed out. In other words, we've hit its max positive charge plus 1. The only thing that we could do is we can take the take oxygen in water and try to burn that. And so under extreme conditions, you can burn it. All right, this is the dozen. So 2 dozen hydrogen, 1 dozen oxygen, 2 dozen waters. It's the same ratio. Or we could do it moles, although we can't draw, because if I did 2 moles of hydrogen, how many molecules would I have to draw here? 2 moles is how many? Number. Give me a number. Yeah, hydrogen molecules. 2 moles of hydrogen molecules consists of how many hydrogen molecules, number-wise? Yeah. Yeah. 12 times 10 to the 23rd, which would be huge. Too many to draw, but we could say 2 moles. We don't use dozen either. Dozen's too small. You couldn't even weigh this on a normal balance. But if we had 2 moles of hydrogen, then you can weigh that on a normal balance, because that would weigh 4 grams roughly. And if you have 1 mole of oxygen, that would weigh roughly 32 grams. And if you had 2 moles of water, that would weigh also 32 grams. Would that be right? Wait. 2 moles, 18, yeah. 36 grams. Let's skip that slide. Now, your book divides reactions into different categories. How many categories did I have for chemical reactions? 3. What were they again? Metathesis? Acid base and oxidation reduction, or redox for short. Your book is going to divide it into combination, decomposition, single replacement, double replacement, neutralization, and then we go on to the next chapter. Next chapter would be precipitation, combustion, and so your book is going to have about 9 categories of reactions. What we're going to use is 3 categories. Of reaction. The reason I'm going to go to 3 categories is because of something called the driving force for a chemical reaction. And so I'm going to deviate from your book a bit. And we're going to look at chemical reactions in the supplement. So these are the types so far discussed here. The reason I'm going to deviate is because combination. We have two different kinds of combination reactions. We have redox combination reactions, and we have acid-base combination reactions. And the redox and the acid-base share different characteristics. And so I don't like to group those both together, because then we'd have to take combination and then subdivide it. But that's okay. We could take combination and subdivide it into the redox and the acid-base. But we're going to do it differently. And then we have decomposition. These are just the redox ones that your book goes through. This is also, single replacement is also a redox reaction. But however, double replacement is not. Double replacement is a metathesis reaction. And so we're going to look at that in that way. All right, and then let's take a look at chapter 9. In chapter 9, I did this experiment yesterday with electrolytes. Except the electrodes, the electrodes could touch. The electrodes are just the wire that they have here, or the copper bars that I had. Let's just take a look at this again. Here, we have non-electrolytes, weak electrolytes, and strong electrolytes. The characteristic of a strong electrolyte is what?
It can, it's a good conductor.
It's a good conductor. Why?
Because it can turn on the light.
Yeah.
It has mobility and it has the charge.
Yeah.
Like high translational energy.
I'm sorry?
High translational energy.
Yeah. Right. It can translate easily. So if we look at copper chloride, this is copper 1 or copper 2 chloride? This is copper 2 chloride, because we have 2 chlorides, copper 2. And so the copper 2 ions represented like this. Usually cations are smaller than anions. The copper 2 is kind of small, it's this white one here. And the chloride's a lot bigger. But when we look at that, what's this structure called here?
Lattice?
Yeah, it's a lattice structure. Does the lattice structure conduct electricity? No, not for this. The electrons are kind of tightly held. Chlorine holds on to the extra electron there. So the electron is not mobile from there. Nor, we look at two types of electrical conductivity. We look at electronic conductivity, in which electrons are the charge carrier. And electronic conductivity primarily occurs in metals or non-metals? Metals. There is one non-metal that conducts electricity pretty well, and what is that? Iodine doesn't. Iodine doesn't. There's one non-metal that conducts electricity pretty well. Graphite. Graphite. But other than that, and graphite conducts electrons. It's not conducting ions. So the electrons in graphite are loosely held and they can move. But that's just because of its unique structure. And so, But something like this, if I put the probes on the solid copper 2 chloride, it's not going to do anything. But what we try to do is dissolve in water. Do you guys remember the rule for chlorides, bromides, and iodides? Chlorides, bromides, and iodides are all, except for,
Iron, lead, and
not iron,
With
silver.
silver. Silver,
Lead and mercury.
lead, and mercury, right. And so copper 2 chloride is not silver chloride, it's not lead 2 chloride, and it's not mercury 1 chloride, so it should be soluble. And so we know it's soluble. The next thing is we have to figure out if it does what. Because strong electrolytes, the way we defined strong electrolytes last time was that strong electrolytes break up and dissociate into the ions. Dissociate into the ions 100% or close to 100%. And so what we want to do is we want to figure out what are strong electrolytes. And we'll talk about these, we'll try to recognize these later, but one, strong electrolytes are soluble salts. A salt is an ionic compound that's not an acid, so this is an ionic compound. And so all ionic compounds are kind of generally categorized as a salt. So soluble salt, copper 2 chloride is a salt. It's not a salt you want to eat, but we call it a salt. A salt is an ionic compound. It's not an acid. And so usually a salt has a metal and non-metal, but not always. Like ammonium chloride is a salt, but it's all non-metals. So strong electrolytes are soluble salts. So copper 2 chloride is a strong electrolyte. It's a soluble salt. And so what that means is it dissociates into the ion. So the water molecules tear apart this lattice. And what do we call this here? This little structure. What's that called? Well, this is where the water molecules surround the copper ion here. What did I call that? Not a molecule unit. It's something else. Hydrated ion, right. The hydrated ion helps stabilize the charge. Do you see what end of the water molecules pointed towards the copper? The oxygen end. And what end is pointed towards the hydrogen end? This is one of the amazing properties of water, and this is one of the reasons they spend, like I mentioned before, that chapter 1 of biochemistry is a chapter devoted entirely to water and its amazing properties. One of the amazing properties is it can dissolve a tremendous number of salts. If it couldn't dissolve a tremendous number of salts, then they say life wouldn't exist. We need water for life to exist. And so this is why when people are doing these planetary and probes out there, the moon included, they're looking for water. So these hydrated ions help stabilize the ions, but these waters aren't stuck on there permanently. There's exchange, so this water can come and knock this water out, and that water can leave. And there's constant movement here. There's constant translational motion. But what's this going to do to the light bulb? It's going to light it up. And so we'll see a bright light here. There are other things that are strong electrolytes. Strong acids are strong electrolytes. Acids begin with the element what? H. In the strong acids, there are 7 common strong acids that you're supposed to memorize. Do you know what the 7 common strong acids are? And they have weaker acids, but these are the strong acids that we want to know. Acetic acid from acetate is not strong. We consider that a weak acid. And so like vinegar is kind of weak.
Hydrochloric.
Hydrochloric. So the 7 common strong acids would be hydrochloric. What's the formula for hydrochloric?
HCl.
Yeah. Hydro means it's chloride, and so it's going to be HCl. That's correct. Hydrochloric is probably the most common strong acid that we use. It can be, but you know, it's like stomach acid. You have stomach acids. One component of stomach acid is hydrochloric acid. It could be dangerous. It could cause tissue damage for sure. They're there. Take a look at that chart on the wall. What's the acid at the top of the chart called? Top left.
Fluoric acid.
Try again. Maybe it's hard to see. Let me
HCl04. That one.
Yep.
Perchloric acid.
Yeah, good. I don't know what happened to my chart. All right, I'm missing it. All right, so you had that correct name. What's the next one?
Hydrochloric acid.
Good. Next.
That's hydrobromic acid.
Good. Anybody else can? Next. We already got hydrochloric there. Next. On the chart up there. Nitric acid. Good. HNO3, nitric.
Sulfuric acid.
Sulfuric acid. Good. How many is that? How many do I have written here on the slide? 6. Number 7 is not on the chart there. The next one after that is hydronium, but hydronium is a special case. It's strong, but it's not an acid that you can just go by. These other ones are acid you can just go by. But Lauren, what was the one you mentioned? Chloric acid. Chloric acid is the 7th. What's the formula for chloric acid? Anybody? HClO3. Good. It's chloric. And so these are the 7 common strong acids: hydrochloric, perchloric, hydroidic, hydrobromic, nitric, sulfuric, chloric acid, in no particular order. All these acids, what they do is they break up into ions. What ions do they break up into? So for example, if I look at perchloric acid, what ions does perchloric acid break up into? It's a strong electrolyte. Strong electrolytes are going to break up 100% into what ions?
Hydrogen, chloride, and oxygen.
Hydrogen
Hydrogen, chloride.
and chloride, like this? Is that the ions it breaks up into? And chlorate? It doesn't seem quite balanced.
Perchlorate, like ClO4.
Yeah, that's correct. The perchlorate doesn't break apart. The perchlorate stays together. And so it forms ClO4 minus. This unit stays together as the perchlorate ions. And so if we look at a solution of perchloric acid, it's going to contain hydrogen ions and perchlorate ions. The hydrogen ions are quite unstable, and those actually react with water to form hydronium. And so we can say it's H plus or hydronium. H plus for short, and hydronium is a bit more stable. And hydronium forms when an H plus and a water combine. When an H plus and a water combine, it forms H3O plus. And that's where the H3O plus comes from on the periodic table there. It's from the formation of hydronium from some other acid, or from water itself. So if I had a solution of HCl, will it light up the light bulb? A solution of all these should light up the light bulb pretty brightly. The other thing we have are the strong bases. One of the strong bases I talked about was sodium hydroxide. Sodium hydroxide is a strong base. But let's categorize the strong bases. What are the strong bases? The strong bases are the soluble hydroxides. Most hydroxides are insoluble, so those we don't consider a strong base. So for example, magnesium hydroxide, is it soluble or insoluble? Well, what's the solubility rules for hydroxide? Somebody tell me the solubility rules for hydroxide. You just read it off. Yeah. The hydroxides are all soluble or all insoluble? Yeah, except for group 1. So the soluble hydroxides would be group 1, ammonium, and calcium, strontium, and barium. So sodium is what? Group 1? Yes? Sodium is group 1. So sodium hydroxide, soluble or insoluble? Yeah. Sodium is group 1. Is group 1 hydroxide soluble or insoluble? It's soluble. Sodium hydroxide is a strong base. Soluble hydroxide is a strong base. Lithium hydroxide, soluble or insoluble? Soluble. Lithium hydroxide is a strong base. Potassium hydroxide. Strong. Rubidium hydroxide. Cesium hydroxide. Soluble, strong base. Magnesium hydroxide, insoluble, Mg. Group 2, but calcium is okay. It's a group 2 also, but magnesium's not. Magnesium hydroxide is insoluble. Is it a strong base? No, it's a weak base.
The way you can memorize is just group 1 and just supposed to be.
Yeah, that's it.
Yes.
And ammonium. And ammonium, right. You done, Cole?
Ammonium is like all of them.
Yeah, ammonium's on all of them. Nicole, did you have a question?
Is it possible for you to write a little bit bigger? I have my contacts in and I'm still having issues seeing it.
Okay. I'll write a bit bigger. This is kind of small here. All right, going back to this. So I asked you sodium hydroxide, strong or weak,
Sodium hydroxide, strong.
etc. And then I asked you magnesium hydroxide, strong or weak, calcium hydroxide,
Strong.
iron 3 hydroxide, okay? The reason why iron 3 hydroxide is weak is because
Is that part of the list?
it's not very soluble. Now, what I mean by weak is very tricky here because I'm mixing up my definitions of electrolyte. And so iron 3 hydroxide is not very soluble. So most of it stays like this. Just a tiny bit dissolves, but what the tiny bit that does dissolve should break up into ions. Iron 3 plus 3 hydroxides.
Maybe it is like less than like 1 mole hydrogen.
Yeah, yeah. It's insoluble.
Like phosphorus.
And so this is what makes it, it's weak because of low concentration. But it's strong because it dissociates into ions. Does it kind of make sense? It's just, yeah, what does dissolve dissociates into ions. Now I have uneven arrows here. The forward arrow shows is small, the reverse arrow is big. And that was done intentionally to show that it's mostly the solid, very few ions in there. Let me add some more pages here. I don't have to write so small. You should memorize the strong acids, the 7 common strong acids is something we should
The
memorize.
strong bases are just sidebar oxides.
Yeah. And there are more. The soluble oxides. The oxides weren't on our solubility rules, but what would you imagine oxides are? Like rust. Is rust, can you wash rust away? Will it dissolve in water? No. Maybe chunks might break off, but it doesn't dissolve. So most oxides are insoluble, right? Now what would you expect the solubility of oxide to be? So let me tell you this. If we look at the size of oxide and compare it to the size of sulfide, which one do you think is bigger, a sulfide or an oxide?
Oxide.
So let's take a look at the periodic table. I got a lot of junk on my periodic table. Oxide or sulfide? Which one do you think is bigger?
Oxide.
How come?
Which is bigger?
Yeah.
You mentioned the picture you drew oxide.
Well, I haven't finished drawing sulfide.
Alright.
But oxide, well, it's going to have 8 protons, 10 electrons. Sulfide has 16 protons, 18 electrons. Which one do you think is bigger, just by sheer number of protons and
I mean, it's sulfide,
neutron?
but no one chemistry fell down the case.
Yeah, chemistry is always tricky like that, but there are reasons for it, then we can figure it out later. It turns out oxide is smaller, sulfide's bigger. Little by little, we'll do it. I'll talk about it later. Which one do you think is going to form stronger lattices, oxide or sulfide? Oxide. Why, Sam?
Oh, I just guessed it.
You guessed it. Does anybody know why?
One by like patterns usually.
I'd rather go by Coulomb's law. Which one do you think will form a stronger lattice?
Oxide.
Oxide because
It's smaller.
it's smaller. There's different ways you could say it. It's more concentrated. Do you see, even though both of them have the same -2, the -2 is going to be concentrated in a smaller volume. And the more concentrated it is, the more reactive it's going to be. Whereas, let's say if you take a gigantic, let's say sulfide's a tiny, tiny, tiny atom. But if you took this and put it on the Goodyear blimp, so you put 2 extra electrons on the Goodyear blimp and you spread those 2 electrons over the entire blimp, is it going to generate much static electricity? No. You know, that was like the Hindenburg. You know, the Hindenburg, they were thinking it was the static electricity that was generated. You know, as the blimp travels through the air, it picks up electrons, and these electrons, and there was a gap, and they didn't properly ground it. So I think if they grounded it, that is, they had a way to discharge the static electricity, which maybe the blimp wouldn't have ignited. But if we only have 2 electrons, we're talking huge amounts of static electricity on the Hindenburg, that was being generated when the electrons get picked up off whatever. It's, there's a lot of friction. And so the more we concentrate the charge, this is huge, it's like voltage. One thing that people do to get higher voltages is they pinpoint it. So they put all the voltage on a tiny pinpoint at the end. And that makes it much more reactive than spreading out the voltage over a large area. They spread out the voltage over a large area. It's not going to be nearly as intense. Here. And so this is just an issue of concentration. The more concentrated the charge, the better. But in terms of Coulomb's law, the distance is, what's the distance between these 2 spheres and these 2 spheres? The distance between those 2 spheres and these 2 spheres is 0. The 2 spheres are touching. And so when we lose Coulomb's law, it's not the distance between the spheres, it's the distance between what?
Force.
The center of the spheres. And so even though the spheres are touching and the distance is 0, the gap here is 0, the distance between the center of the spheres is different. Do you see that?
That's what makes it more concentrated.
Yeah. And so the concentration works. We can just think of that in those terms. So oxides will have a stronger lattice. And so if sulfides, the soluble oxides are probably going to be just what?
Group 1.
Yeah, group 1. Maybe a group 1 in ammonium, but ammonium oxide, I don't think you're going to find. But we'll just say group 1 in ammonium. So there's a case where we want to see the pattern and then be able to make some kind of prediction. We were trying to make predictions. We're trying to minimize the amount of memorization by trying to figure out other ways of figuring things out. And so the soluble oxides are strong bases. And the soluble oxide is, what was the oxide, the formula for oxide? O2, positive or negative? Negative. And the amides are pretty much all soluble. And this is an anion that I haven't talked about, but this is called the amide ion, or the amide. This one you don't have to memorize.
Soluble amides?
Amide. Soluble amides. All of them are soluble, so we don't really have to worry about it too much.
Is it like on the ammonium hammer? Goes like that?
Yeah,
It's like NH with 3 minus?
right. It's a ide ion of ammonia. Usually we do ides of elements like chloride, but this is ammoniide, but formula is different though. It's NH2 minus. Take a look at the bottom right of that chart up on the board. Do you recognize the ion on the bottom right?
Ammonium?
No. Bottom far right.
The NH3 was the N plus?
No, yeah. What's the thing on the furthest right?
Dioxide.
NH2 minus. What's that called?
Nitrogen nitrogen dihydride or something like that. Is it amide?
Yeah, amide. Amide. What does it say to the right of that?
Bottom right, right?
Yeah.
Which one?
Just to the right. Just to the right of amide. What does it say?
Very strong base?
Yeah. What's above amide?
Fairly strong?
Above the amide, the ion. What's above? What ion is above that? Hmm?
Hydroxide?
No. Right above, directly above amide. Directly above amide is what? Oxide. And directly above oxide is hydroxide. But do you see that one that's circled in black with an arrow going down? That is stronger than hydroxide. This chart's old. And so the more recent data is this. This is in no particular order here, but if you want the order, you can just go to the chart. The soluble sulfides. Somebody tell me what the soluble sulfides. Most sulfides are insoluble except for which ones?
Soluble sulfides?
Yes. Group 1, Group 2, and ammonium. Those are all considered strong bases. Everything else is weak, considered weak. So in a typical class like Chem 4, you're asked to memorize the 7 common strong acids, but the reason is then you can recognize strong ones versus weak ones, but you aren't going to be asked to memorize the strong bases.
So we don't memorize it?
You don't have to memorize the strong bases. Make an effort to memorize the strong acids, though. You make an effort to memorize the solubility rules. You're going to have to predict some reactions. The way to memorize it is start early and just read them like 2 times a day or something, 3 times a day.
Or no? The charge on that is 2+, right?
Charge on what?
Lead?
Yes. Weak electrolytes will dimly light up the bulb. And the weak electrolytes are going to consist of the weak acids. The weak acids, what are the weak acids? Do you have to memorize those? No, you don't have to memorize those. The weak acid is any, this is acid that is not strong. The problem with this is that there are more than 7 common strong acids. And so that makes it more difficult, but you're not going to encounter those. So exceptions exist. Outside of this class, exceptions exist, but this class is more like more controlled,
Yeah.
right? Because
Kind of like math where it's like no other proofs, just need to calculate.
right, it's kind of like this. It's like you know, if you're learning how to drive, are you going to automatically start driving all over LA? Let's say probably not. You probably want to start in a more controlled environment, You don't want to just jump into heavy traffic and high speed and this kind of stuff. And so the same thing here. We just try to make it more of a controlled. So weak electrolytes are going to be weak acids, weak bases, and some heavy metal salts. But it depends on how you're defining weak electrolyte. Weak electrolyte here, the way we're defining it is partial dissociation. But it could also be like a weak or dim light bulb here. It could be a strong electrolyte, but with limited solubility. Like lead-2 iodide. Remember the lead-2 iodide we looked at? Yeah. Some heavy metal salts, it's like the higher charge, like lead-4, you know, that kind of thing.
Could you redefine partial dissociation?
How do you define partial dissociation? This is acetic acid here. And acetic acid, the H can split off and leave us with acetate. And so acetic acid breaks up into, let's take a look. I'm going to write the uneven arrows. The small forward arrow means it's not very favored in the forward direction. The big reverse arrow means it's much more favored. So it tells us which side's favored. This side's heavily favored. And so when I look at a solution of this, most of the acetic acid has not split apart. This one split apart. Sorry, this one split apart. And so out of all these, most of them have not split apart. This one split apart here. The rest are not broken apart. So this one's good, 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 good. So 1, 2, 3, 4, 5, 6, 7. 7 that haven't lost the hydrogen. The hydrogen on this end here. Do you see this hydrogen on the right end here? This one's missing that hydrogen because it broke apart here. And so this gives an imbalance here. And what happens is we could have a lot of acetic acid, but does acetic acid conduct electricity? No. Why? No. It doesn't conduct electricity because it has no mobility, or does it have mobility? Does acetic acid have mobility? Yes. It has mobility. Acetic acid doesn't conduct because there's not enough number? N? No, acetic acid doesn't conduct electricity because it has no charge. Electrical conductivity depends on 3 things. What are those 3 things? Yeah. Right. And so when something doesn't conduct, think of those 3 things. Don't think of other things like that could be related, but you'd have to make an extra step or 2 to make them related. And so we expect low conductivity because of why? Well, the acetic acid molecules aren't conducting. What's conducting? So we're going to ignore this. It's like water. Is the water going to conduct electricity? No.
It's ions.
Right. And so what's going to conduct electricity here will be these.
That's very few.
So these have charge. You see the positive charge here and the negative charge here. They have charge. Do they have mobility?
Yeah.
What's missing? The number. The number is very small. And so this is why the electrical conduction is not so great.
Very few ions is the problem.
What's that?
Very few acetate ions.
Yeah, very few ions is the reason why. They have very few ions because it's a weak electrolyte. Weak electrolyte's only partially ionized. If acetic acid were a strong electrolyte, if acetic acid were a strong acid, it would conduct electricity very well.
Any non-electrolytes?
Yeah, non-electrolytes we have to talk about next. Uh-huh, Nicole.
Sorry, I was making a stupid question, you may have covered it already, but, you said that the water doesn't conduct the electricity?
Yes.
What conducts electricity in water when it does?
Things that are dissolved in the water. The water molecules themselves don't conduct electricity. The water molecules themselves don't conduct electricity because
Has the charge?
it has no charge. Yeah.
So water is a base, right?
No, water is a very interesting compound.
Yeah, water is the
Yeah, water, we're going to talk more about the properties of water. Water is both an acid and a base. It has like a dual. This is one of the other unique properties of water. Water can act, you know, some things have a preference, but we call things that can act both as an acid and a base as amphoteric or amphiphilic. And water can go either direction equally as well, which gives us another important property for life. And so water is pretty amazing. But one thing water can't do is it can't conduct electricity pure by itself because there's no charge. Non-electrolytes are everything else. If it's not a strong electrolyte and it's not a weak electrolyte, then it must be a non-electrolyte. So if I have ethanol, is ethanol a strong acid? Yes or no? No, it's not one of the seven. Is it a strong base?
Yes.
No. Is it a soluble salt? No. Is it a weak acid? No, it doesn't begin, ethanol doesn't begin with H. So it's CH3, CH2OH. But later on we'll learn it could potentially be an acid. But we don't really classify it as such. It's so weak. Is it a weak base? No. Even though it looks like it has hydroxide, that's not hydroxide.
For example, phosphorus or phosphate would be a non-electrolyte.
Phosphorus?
Phosphate.
Phosphate? Phosphate is an electrolyte. Like sodium phosphate is excellent.
That's what I read yesterday.
Hmm?
We had the metal by itself. It was an aqueous.
Phosphate?
Yeah.
Aqueous?
You know, solid.
Solid? What was the solid? You can't have phosphate alone. It has to have some cation. What is it? Well, we'll come back to that. Phosphate is an excellent electrolyte, actually. It can conduct very well. It's not a weak base, it's not a weak acid, it's not a heavy metal salt, therefore it's a non-electrolyte. So we just do process of elimination. If we know what strong electrolytes are, we know what weak electrolytes are, then everything else should be non. What non-electrolytes do is they don't split apart. So ethanol molecules don't break apart. And so when I look at all the ethanol molecules here, they're all intact. If they're all intact, everything has a neutral charge, and if everything has a neutral charge, is anything going to conduct? No, and so conductivity is 0. All right, let's stop here. We'll take a break, and then continue after the break. All right, we'll get started again. There are different places for help. Mesa and the library offer tutors. But there's also office hours here. I had to change my Monday office hour. But I also have this night one here. I don't know if that's a convenient time or not. Does that work for people that late? I might bump it up a little earlier. That makes it easier. Or I can change some of the other hours to make it more convenient. But you're always welcome to come there, and I'll try to help you out with the material. All right, so again, there's a little bit of a mix-up when it comes with electrolytes because it depends on, if you get a dim bulb, what does that mean? Does that mean you have a strong electrolyte that is, it breaks apart but it's not very soluble, or is it, a weak electrolyte? Yeah, it's hard to tell the difference, In terms of electrical conductivity, it's easy to tell. If the bulb is dim, it's weak. But you could have weak conductivity. Here's some definitions. Electrode are the conductors by which the electric charge enters and leaves electrolytes. Electrolysis has different definitions, though. When we talk about the electrolysis of water, that's like taking water and breaking it up into hydrogen and oxygen. But these two definitions you don't need to know. I wouldn't bother with those. Conductivity in an ionic solution here. This is just kind of repeat. You can see that one of these electrodes is positive, and the positive one's going to attract which ions?
Negative.
The negative. So these green ones are the negative. And we'll have an electrode over here that's negative, and that one's going to attract the positive cations. And based on this, we have movement of charge. The negative charge is moving to the right, the positive charge is moving to the left. That's electricity, movement of charge. Electrolytes and conductivity. Strong electrolytes are going to have good conductivity, for sure. Weak electrolytes will have poor conductivity, but you get poor conductivity due to having a strong electrolyte at very low concentration. And you could also have no conductivity if you just don't have enough charge carriers. That is, you might have a strong electrolyte there, but it's so dilute that it doesn't really conduct. But the way we're going to define it is 100% dissociation. Another word for dissociation is ionization. It's forming ions. So if you take copper 2 chloride, it's going to form the copper 2 ions and the chloride ions. And so complete ionization or dissociation. We use these terms interchangeably, ionization and dissociation. Although ionization is used in other senses and other ways as well. So there are multiple definitions of ionization. This is one involving the dissociation into ions. Weak electrolytes have limited or partial ionization or dissociation. And non-electrolytes have no ionization or dissociation. So non-electrolytes, no. So sodium chloride, is sodium chloride soluble?
Yes.
Yes.
Not as a solid though.
Yeah, it's not going to conduct electricity as a solid, but if you dissolve it,
Yeah.
it will. And so this is called dissolution. Dissolution is just dissolving. I don't know why they don't call it just dissolving. But dissolution means dissolving of sodium chloride. So when we dissolve sodium chloride, does it break apart fully, partially, or not at all?
Fully.
It breaks apart fully, and so that's what we call a strong electrolyte. Copper 2 chloride, because it's a soluble salt. Copper 2 chloride, is that a soluble salt?
Yes.
Yeah. And when we dissolve it, under the dissolution process, it breaks up fully into the ions, copper 2 and chlorides. There. Here's the dissolution of sodium chloride. So you recognize this structure here, right? That's the
Last.
lattice. So if you have a positively charged marble, then you want as many negatives around it as possible. And if you have a negatively charged marble, you want as many positive marbles around it as possible. So there's a lattice structure. The water can break it apart. And so this is just a static image of this. There's lots of motion happening here. You can see the hydration. You see the hydration? We call this the hydration sphere, what they outline in yellow here. And that helps stabilize the ions. Otherwise, the ions are kind of reactive. They'll want to come back together or hang out. But the water is going to surround that, just help stabilize it. Same thing with copper 2 chloride. This is copper 2 chloride pentahydrate. I can tell it's the pentahydrate because it's got the deep blue color. So there are water molecules stuck in the little crevices here. Those crevices we give another name to. What was the name? Does anybody recall the name? The little cracks and crevices in the lattice structure.
Is it crystallized?
It's a crystal, but in the crystal there's little gaps here. Little gaps here in the crystal. And what are those little gaps called? We don't call them little gaps or crevices or cracks. We give them a specific name, and this is the name that is used. Starts with an H. You have it? H-O-L. H-O-L-E. Holes, yeah, they call them holes, but they're not really holes. Do you see holes in the lattice? Not really, but that's what they call them. They call them
Very anticlimactic.
yeah, holes. Yeah, I know, but yeah, I mean, and so the water molecules get stuck in the holes. And so this is a hydrate. They don't show the hydrate, the water molecules stuck in there, but then they dissolve it. Strong electrolyte. Write the dissolution. Here they call it dissolving. Dissolving dissolution. Most people will call it dissolution. But here, this is a potassium salt. All potassium salts are soluble, or all potassium salts are insoluble?
Solid.
All potassium salts are soluble because potassium is a group 1. Group 1 salts are soluble, group 1 ammonium. So I already know this is soluble. Soluble salts are strong electrolytes, weak electrolytes are non-electrolytes.
Strong.
Strong. So it's soluble, and when it dissolves, it dissociates into the ions. Now the sulfate doesn't break apart. Sulfate just stays together. Potassium's there. All nitrate salts are soluble. So calcium nitrate will all break apart. And the nitrate stays together like this. So we form calcium. And we've got to make sure it's balanced. There are two nitrates, so we've got to make sure. There are two potassiums.
Calcium nitrate, that's in this solid state, right?
Yeah. Calcium nitrate is supposed to be solid state. This is some kind of typo here, or maybe they're missing the arrow. There's some stuff that's missing from here. And so let's put that in. We put parentheses solid to indicate it's a solid state, and then we'll put an arrow. This is not like a double arrow because it's just one way. It's going to dissolve. Yeah. So let me fix that slide.
And if you boil the water, for example, you leave the ion behind would form the solid.
Yes. What happens is the ions stay apart from each other. We'd like to be independent or hydrated, like this. So the water molecules tear apart the lattice. If you start removing the water, then it's like, these are like caged animals here. They want to kind of stay apart from each other, but as the cage gets smaller and smaller, you have to force them together. And the only way to force them together is get rid of the water entirely. If we get rid of the water entirely, it'll revert back to the crystal, and then we'll have the solid remain. But that's only if there's no water. Otherwise, the sodiums and the chlorides like to be free in the water, like that translational mobility. Some ions don't. Some ions don't want to be free in the water. Some ions want to be in the lattice, and those are the ones that precipitate. So this is what we call an unfavorable ion combination, because the only way to get these two ions to combine is to get rid of all the water. And so you just shrink the cage down smaller. The other ions are like this. They're free, they're mobile, and as soon as they see one another and come into contact, they precipitate. And that's what's happening with white solid that we saw in the test tube over there. Those are highly favorable. This is not favorable. Yes, sodium chloride, yeah, this is a stable compound, but same thing here. The only way to get the copper and the chloride to come back together is to get rid of the water. Which you can do. It's easy to do. Acids. We call H plus a proton because if we look at hydrogen, hydrogen 1 consists of one proton and one electron. So if we remove the electron, we form the hydrogen ion. Hydrogen ion only consists of one proton. A proton, how big is a proton compared to an atom? How many times smaller is a proton compared to an atom? It's like 10 to the fifth. The analogy is if the proton were like a centimeter, then the atom would be like a football field. If you blew up the proton to be 1 centimeter in diameter, let's say you zoomed in and it's 1 centimeter in diameter, then the atom would be how big in diameter? The atom would be like a football field big, like 100 meters or 100 yards big. I'm sorry? 10 to the fifth. 10,000, 100,000? 100,000 times bigger.
Angstrom was what? 6 angstroms.
Right. Right. And the nucleus is going to be much smaller. And so the cation's H plus, the anions X minus. This is just generic, so it could be chloride, bromide, iodide. The cation's H plus, the anion would be X2 minus. This would be like sulfide, oxide, whatever. And here we have 3 minus, like phosphate, nitride. This is an acid plus water. Water is kind of interesting because it can go either way. And in acid-base reactions, what we have is we have different types of acid-base reactions. And maybe the easiest acid-base reaction to understand is the Bronsted acid-base reaction. In the Bronsted acid-base reaction, we transfer the proton, the H, from the acid to the base. And so bases are proton acceptors, acids are proton donors. And so what happens is we lose the H plus, it goes to water. When the H plus goes to water, it forms hydronium, and then we're left with X minus. And so this is a Bronsted acid-base reaction in which we have a transfer of a proton.
The oxygen is a positive because there's one more hydrogen, correct?
Not the oxygen, this ion, hydronium ion. This is called hydronium. H3O plus is the hydronium ion. And the whole thing is positive. It's not just the oxygen.
So we need H4O2, cancel it out.
H4O2? No. I mean, it would just be this. Just this is it.
I mean, like, we want to get rid of the positive to make it neutral.
Okay, yeah. Then if we want to make it neutral, we have to get rid of one of these. We got to get rid of the H plus, and we can't. We just reverse
So
it.
we wouldn't be able to add another hydrogen oxygen?
No. No. You can't on this one. You can link them together, so we'll have multiples of this, like H6O2 plus 2 kind of thing. I think. Water is a weird species. And so water can also act as an acid too, but in this case it's a base. And so we probably should have talked about acids and bases first. Acids are proton donors, bases are proton acceptors. So here's what's this acid? Hydrochloric acid reacting with water. What's this one?
That's
Nitric
nitric acid.
acid, good. Nitric, reacting with water. These are all examples of acid-base reactions.
Remember you said acids are what donors? Or
Hydrogen ion donors. A hydrogen ion is called a proton. And so acids are proton donors. Bases are proton acceptors. Water can go either way. And so this is acid. This is base. Water can go either way, and which way it goes depends on what you react it with. So if you take water and react it with an acid, then it'll act as a base. If you take water and react it with a base, then it'll act as an acid. This is the acid, this is the base. In this type of reaction, we take a H plus from the acid and give it to the base. And so we call this a proton transfer reaction. And this is what we label as a Bronsted acid-base reaction.
Bronsted?
Yeah, Bronsted acid-base reaction. Water is not the only base. We have lots of bases that we can use for these acids. Remember what I called HSO4 minus? HSO4 minus is called a acid anion. It's an acid anion because it's an anion, negative charge, that begins with an H. Acid anions are interesting because acid anions can go either way too. If you take an acid anion and react it with an acid, then the acid anion is a base. Or if you take an acid anion and react it with a base, then the acid anion is a...
But it has to start with S for it to be an acid anion?
What starts with an S?
It has to contain S, is that what you...
No, that's not what I said. It has to, acid anion has to have a negative charge and begin with H. That's what I said. In this case, the acid anion there is acting as a acid or a base. It's acting as an acid because it's losing H. Acids lose H, bases gain H, and so water is acting as a base. So if I look at my acid anion, then it just makes, we go from this, what's this called? I mean, the name.
Acid?
It's an acid anion, but what's the name of this acid anion, this particular acid anion?
Uric acid?
No. Sulfuric acid is not a charged species. Sulfuric acid would be a neutral species. No, hydrosulfuric acid, hydro means it's an ide, not sulfurous acid.
It's,
Oh, I'm sorry, not this one here. Sorry. This is sulfuric acid. This is what?
it's silicate and hydrogen.
There's no I. Silicate would require an I.
It's sulfate.
It's sulfate, but it has a H plus stuck on there, so we call it not di. Hmm? Hydrogen sulfate. That's a hydrogen sulfate ion, AKA, not di, bisulfate. This is bisulfate here. This acid has two acid hydrogens, and since it has two acid hydrogens, we call it diprotic acid. Protic for the proton. H plus is the same as a proton. The most common isotope of hydrogen is H1, and so H plus is just a single proton. If I'm looking at deuterium, then there would be a neutron and a proton, so we wouldn't call it a proton. But if I'm looking at hydrogen 1 losing an electron, then all that's left is a proton. And so we call this a proton. And so H2SO4 is diprotic acid. It has two protons that it can donate. And so we do it in two steps. The first step here is water will take the first one. When water takes the first one, we form hydronium and bisulfate. And then bisulfate again can lose one to water. And then we'll form hydronium and sulfate. So this is diprotic acid there. Now, this looks like a tetraprotic acid, doesn't it? What is this acid called?
Acetic acid.
Acetic acid. It looks like a tetraprotic acid, but it's not. It's a monoprotic acid. It's a monoprotic acid because the other three hydrogens structurally can't react as an acid. And so we separate these. Three of these hydrogens are different than this one. Only this one is acidic. The other three are what we call non-acidic hydrogens. And non-acidic hydrogens is just what it's bonded to. When we look at the formula like this, it doesn't really tell us the structure. This first hydrogen is actually bonded to the oxygen. These other three hydrogens are bonded to carbon. That makes a world of difference in its reactivity, whether the hydrogen is bonded to an oxygen versus hydrogen bonded to a carbon. And not only that, it depends on how that oxygen is structured. You know, what is that oxygen itself bonded to? And so, even though this looks like a tetraprotic acid, this is only a monoprotic acid. And the other three hydrogens don't react. And so just this hydrogen, this is an acid, so it's a proton donor, donates the hydrogen to water, forming hydronium. And then we're going to be left with acetate. The acetate itself doesn't split apart, nor is acetate an acid. Have you heard of pH? Yeah, the acidity of water. It's the power of the hydrogen ion in water or hydronium ion. And so all these will impact the pH because the more hydronium you have, the higher the concentration of the hydronium and the lower the pH. There's an inverse relationship between hydronium and hydrogen ion and pH. And so these are all going to change the pH of water. pH is very important in life. You know what the pH of blood is? The pH of blood is close. 7 is neutral. It's just slightly above 7, which makes it slightly basic. But if the pH of your blood changes just by a little bit, do you know that's fatal? You know, the pH of blood has to be maintained.
Below 7, it's acidic.
Mm-hmm. And that causes a lot of trouble.
What happens when it goes to like 10?
Oh, you're dead. It would never go to 10. You would be dead. If it goes like from 7.2 to 7.4, then there's some serious trouble. You know, some minor change, you think it's minor, but it's serious trouble. This is, we see here. So is sulfuric acid a strong acid?
Yes.
Yeah. Let's take a look at these acids again. Here. Is hydrochloric acid a strong acid?
Yes.
So this goes 100%. Is nitric acid a strong acid?
Yes. Yes.
So this goes 100%. This is called ionization or hydrolysis. This is what happens in water. Sulfuric acid? Strong acid?
Yes.
100%. Now this is split up into two. Is bisulfate one of the 7 common strong acids that you memorized? Bisulfate, is it one of the 7 common strong acids that you memorized? No, it's not. And so this is a weak acid. Weak acids only do what? Do they fully ionize or partially ionize or not ionize at all? They partially. So I'm going to draw a second arrow here. This is showing kind of full ionization. It's not full ionization. It's only partial ionization. And so the bisulfate doesn't break apart to a significant extent. If you want to know, in Chem 1B you do these kind of calculations. About 10% of it, 90% will stay as bisulfate, and about 10% of the bisulfates will break apart like this. And that percentage changes depending on what the weak acid is. So if we look at this acid, what's this acid's name? Acetic acid. Is it one of the 7 common strong acids that you memorized? No. Therefore, this is going to partially dissociate. And if I look at the percentage, it's only like 0.01%. So 99.99% of it stays like this, and only about 0.01% changes. That percentage changes depending on the concentration, so we can't just use a percentage. And so really the reverse arrow is much bigger. Here. Because this is weak. And when we say partial, it's not like 70%. Well, it depends on how weak it is. Like some of the stronger, like phosphoric acid. Is phosphoric acid one of the 7 strong acids that you memorized? No. So phosphoric acid is like 70, 80%. This is one of the stronger weak acids. And so maybe it's like 70% ionized. But this is really weak. This is only like 0.01% ionized. And so there are varying strengths of weak acids, from the stronger weak acids to the weaker weak acids. And what dictates how strong they are is the percent, or how much it ionizes, like percent ionization. You know, strong acids have a very high percent ionization, or dissociation, or what we call hydrolysis. What some people do is they just make this, like these equations here, like this. This is a hydrolysis, this is an acid-base reaction. They just write this in shorthand without the water. If they remove the water, then they'll get H+. But a proton is, you know, I talked about concentration of charge. Protons don't exist in water. That's because if you look at a sodium ion, it's pretty big. What's smaller than a sodium? If we look at a lithium ion, it's smaller. But if we look at a proton, how big is a proton? So this might be like a football field or something like that, but a proton would be just like this tiny dot. This would be a proton. So if I'm looking at all three of these have the same charge, but they have different concentrations or charge density. So which one has the highest concentration of charge? The proton. And what that does is it makes it unstable. So for lithium ions and sodium ions, we could have hydrated ions. And the water molecules will just surround the ions like this. And will form hydrated ions. But the proton won't form hydrated ions. The proton is going to react with the water molecule to form, this is my H plus, to form H3O plus, hydronium. However, sometimes we don't write hydronium. Sometimes we do this in this kind of shorthand convention. So a lot of times we'll just write it like that. Strong acids completely dissociate. Weak acids will partially dissociate. Strong acids completely dissociate. So the major species in strong acid solution will be the ions. The minor species will be the molecule of acid, like HCl molecules. They should be 0 to 100%. But for weak acids, you'll have major and minor species, depending on the percent ionization. If the percent ionization is less than 50%, then the major species will be the molecules and the minor species will be the ions. If it's greater than 50%, then it flips. It's weak acids. So we have a strong acid like hydrochloric acid. Hydrochloric acid is going to consist of, well, HCl. HCl is a strong electrolyte. It completely breaks apart. But if it completely breaks apart, it's going to form a proton. The proton, is it going to be stable? No, it's going to react with water to form hydronium. So we could just do it in one step. Or we could do it in 2 steps. And so I like to do it in 2 steps like this. I'd like to do HCl, strong electrolyte. It's going to break up into H plus and Cl minus, but we know H plus aqueous isn't so stable. It's very reactive because of its high charge density. So the H plus aqueous is going to react with water to form hydronium. And then what we could do is we could add these 2 equations up. If we add these 2 equations up, then what we get is HCl. Do you see the H plus cancels? We have H plus on the right side, H plus on the left side, that cancels. So we have HCl plus H2O liquid. This is going to give us H3O plus and Cl minus. And so the H3O plus is the hydronium ion shown here. And the Cl minus is the chloride ion shown here. And so we have hydrated hydronium ions. Do you see that? Here, here, here. And we have hydrated chloride ions here, here, here,
So
here.
the idea is that the water, if there's a proton like hydrogen, it'll just pick it up and everything else remains.
Yeah. Over here, this is acetic acid. Acetic acid is weak. So the major species over here are just the ions. Over here, though, the major species are the acetic acid molecules. Most of the acetic acids don't dissociate. It's just a very small percentage that dissociate. So this would be the major species, the acetic acid. And the minor species would be hydronium and acetate. And so we have some acetate here, here's some acetate here, and then we have some hydronium here. That would be the minor species. I know on the lab they ask you for that, but some of those don't make that much sense. Hydrochloric acid is strong acid. What is the name of this acid? what's the anion?
Hold on.
Is the anion an ide, ate, or ite? Fluoride. And so if we have an ide, it's always got to be hydro.
Hydrofluoric acid.
This would be hydrofluoric acid. Hydrofluoric acid is the odd one of the bunch, because what did we say about hydrochloric acid?
Hydrochloric.
Hydrochloric, is that strong or weak?
Hydrochloric.
Strong. Hydrobromic acid,
Strong.
strong. So hydrochloric acid, strong. Hydrobromic acid, strong. Hydroiodic acid, strong. What happened to hydrofluoric acid? Why isn't hydrofluoric acid part of the group? Yeah. It's out of the group. Why is it out of the group? It has to do with the size. You know, size can impact things.
It's not as big as the rest.
Yes, not as big. It's the fluoride. The fluoride turns out to be a little bit more reactive. It doesn't want to let go of the hydrogen as easily as the others. The others will let go of the hydrogen a lot easier. Fluoride wants to hold on to the hydrogen, making it a weak acid. You know. In order to be a strong acid, it has to let go of the hydrogen easily so that we can make lots of hydronium. But it doesn't. And so oddly enough, it's weak. But even though hydrofluoric acid is weak, it's a weak acid. So a weak acid would be like a vinegar, you know, acetic acid. And you wouldn't think much of it, but hydrofluoric acid has, in addition to its acid properties, it also has metathesis properties. And so hydrofluoric acid is do you ever watch those crime shows? Or hydrofluoric acid is used by criminals to do what? Do you know? Yeah. To dissolve what? Bodies, right? Huh? You don't want to make it at home, I don't think. Flesh-eating hydrofluoric acid. Yeah. Should we watch it? Not that you want to do this at home.
Most chemists are fascinated.
So even though it's a weak acid, doesn't mean it's not reactive, because when we think about chemical properties, we think about three types of chemical properties. What are the three types of chemical properties? What? This doesn't have audio. I forgot my computer is not connected to the audio here. Let me do it here. Yeah, it's the guy again, right. The guy is a professor at the University of Nottingham in England. Hydrofluoric acid. This guy has a series, the periodic videos. So if you want to learn about the periodic table, this is pretty good. Ooh, cheeseburger and hydrochloric acid. I haven't seen that one. Hydrochloric, not fluoric. I don't think it's going to do much. A cheeseburger and hydrochloric acid is not going to do much. But let's see what the hydrofluoric acid does to this. Let's see what's wrong with this. No. what's wrong with the audio now. Do you hear the audio?
Now, obviously, human flesh, and Brady decided that the chicken's leg, that the uncooked leg of the dead chicken, is
Where you going?
This audio is crazy here. Each day it's going through something different.
Brandon, how much is sodium in a block of sodium metal?
It's not that expensive.
There you go.
I used to use a lot of sodium, so I used to buy it by the cylinder of sodium. It wasn't that expensive. But you can't just go to the store and buy it, though. I mean, they don't sell it at Home Depot. You have to have an account.
Isn't that like elements, just like raw elements like that?
What's that?
Like a store, and so they can have an account?
Yeah. It's like there's one place in Gardena here. It's called Spectrum Chemicals. You can buy it there. They're kind of expensive. There are other places, Aldridge Chemical, a whole bunch of places you can get it. But some chemicals they won't sell to you unless you have like for example, you can buy cocaine from Aldridge, but you have to have like some special, laboratory.
Is it Breaking Bad?
Yeah.
I was thinking of that too. It must be Heisenberg.
All right. The audio's not working. Do you want to just see the video?
Yeah.
We'll just fast forward to it and let's just go to the end result. Let's see what happened to the chicken leg.
Isn't it a laptop?
What's that?
Isn't it connected to the laptop?
No, it's not connected to the laptop. Let me see. Oh, you're right. It is connected to the laptop. That makes sense. Okay. Now let me see if this works.
most chemists are
Do you hear anything?
leg, that the uncooked leg of the dead chicken is a reasonable approximation to a decided that we can try and do a demonstration for which
So it's HF, HCl, and sulfuric.
After half an hour, nothing.
It also depends on the concentration.
At the end of the day, something slightly might have happened. We decided to call it a day, but just in case to leave it overnight in the atmosphere. In the morning, it was really the two chicken legs in the coal acid, HCl, sulfuric acid, had made quite strong colour in the liquid. And the bits of the chicken legs sticking out still look quite healthy. You could almost imagine cooking it. But the leg in the HF was pale, looked decidedly dead. So we lifted them out. The one HCl and sulfuric acid, it turned rather jelly-like. And really looked almost like an advertisement for being a vegetarian. Really yummy. But with the HF, it was quite different. It was as if the surgeon had cut the bottom off. It was moderately interesting what had happened below the surface, but really what was much more interesting to me is why the chicken leg in HF looked as if it was dead. And clearly what had happened is that some of the pigment, some of the red colour had been eaten away. The reason it is red is because it contains a molecule called myoglobin, which is related to hemoglobin, which we have in our blood. And myoglobin stores oxygen in muscles. And myoglobin is a very similar colour to hemoglobin. If you cook beef, roast beef that's rare, and red juice comes out, the red juice is myoglobin. When in fact myoglobin reacts with carbon monoxide and makes it such a bright red. My theory is that the HF is leaching away, that's attacking the structure of the myoglobin, in particular the so-called heme group, the iron porphyrin group in the middle, and breaking some of the bonds so that it no longer feels like others. And that's why the solution that is left of HF was completely colourless. It looked as if the stuff had just disappeared. There wasn't any sludge in the HF beaker. Well, it's cool. I thought acid was acid. I always learned that H plus is a big deal in the journal work. Whether H plus is coming from like uric acid, sulfuric acid, or sulfuric acid. What's the phrase? Don't do their work for chicken leg? The reason is that the chicken leg is made of a mixture of organic compounds, proteins, different fats, and also bone, which is a mixture of minerals. Now, if you break these organic molecules, you are breaking carbon, hydrogen, carbon bonds. And you can't just break them, you have to, if you like, catch them off with some other group. And carbon and fluorine bonds are very strong. In fact, HF is not a very strong acid. If you dissolve HF in water, especially when it's dilute, which is not as acid as HCl because the bond doesn't dissociate the HF bond quite so much. But hydrogen fluoride HF is very reactive because although the bond is strong, the bonds in the
guess that wasn't so dramatic. But what is pretty dramatic are, you know what they use HF for a lot? Etching semiconductors. And so UCSB in the electrical engineering department, they have the wall of horrors. Electrical engineers maybe don't have as much lab skills as some other sciences, but they have a lot of accidents there. And some of the most gruesome accidents are HF burns to the eyes. Yeah. You can see, I mean, you don't want like sulfuric acid or whatever else. But I think they removed these from the internet, though. One of the suppliers, manufacturers of HF, posted. You don't have to look at don't look at these images, but yeah, HF burns to the eyes are nasty. This is HF burns to the fingers.
Are you like getting directly in your eye or like?
This is like permanent blindness right here, just splashed into the eyes. HF splashed into the
I will
eyes.
never become a chemist.
What's that?
I will never become a chemist.
Most of these are not chemists. Most of these are electrical engineers working on etching semiconductors and that kind of stuff.
Skill issue.
Hmm?
Skill issue.
Yeah. It's nasty. I mean, some of these burns are just horrendous. Look at that.
That's why you wear goggles, right?
That's why you wear goggles, and then with HF you got to be especially careful. There was HF is used for cracking in refineries too. So and there still is a petition because there's a refinery on Crenshaw here. Have you seen that? The petition to get them to look for alternatives to HF. You know, there was an HF. Basically, if they have an HF leak, then there's supposed to be bars going across Crenshaw to prevent traffic from going through and that kind of stuff. And then evacuation around a certain perimeter. Apparently, they did have an HF leak, and somebody was driving on Crenshaw. Did you hear about that? Yeah, okay. Yeah. But it's a weak acid. You think it's a weak acid? Well, it's got metathesis. It's not the fluorine, it's the fluoride in HF. The fluoride is very reactive chemically.
So if there's a leak and it's gas, I mean, how are they supposed to?
You're supposed to keep your windows up, turn off fresh air from coming in, just have it recirculate.
Like, how do they control it by putting up when it just get out?
Yeah, and then it dilutes, and it's pretty reactive, so it'll start reacting with stuff, you know.
Because I live right by there. We
Oh,
have all
do
the
you?
signs. Like, I live in Old Torrance, but there's
Oh.
signs on everybody's yard. Like,
About the
you
refinery.
hear it all day, all night.
Yeah. So yeah, you want to be careful with HF. I know there's that issue, but I think they can have certain control measures so that the risk of leak is minimal. You know, you just need to control, and so you need like backup plans, those kind of stuff.
The iron bars, they look like the lawnmower with Matthew. Is that what you said?
What's that?
The iron bars, they look like the lawnmower with Matthew.
No, and I think they used to have these gates, but I don't think they have those anymore. I think it's just open, but they must have something. Yeah, so the residents that live around there are, I'm sure, concerned. You know, it wouldn't be good to have HF leak anywhere. So just because it's a weak acid doesn't mean it's unreactive, because there are three types of reactions. And so when we look at a chemical, we look at the acid base. Acid, it's not a very strong acid, so okay. But what about its metathesis properties? And metathesis, fluoride's quite reactive because it's small size, makes it more reactive. Fluoride in small concentrations is fine. You know, like toothpaste. You know, toothpaste, they put fluoride in there, and fluoride reacts with your teeth to make it a little stronger. There's a more favorable. It gets rid of the hydroxide. There's hydroxide in your teeth. There's calcium, phosphate, and hydroxide. I think they call it calcium hydroxyapatite, or whatever. But if we can replace the hydroxide with fluoride, it makes it more stable, and so your teeth are going to be stronger. But in high concentrations, you know, so like at low concentrations is fine, but at high concentrations, your teeth will start to mottle. That is, your teeth are going to start getting eaten away. Uh-huh.
So the type of reactions, you said we only have to focus on like 3.
Yeah.
Which ones would they be?
Somebody help me with that.
What was the first thing you mentioned in the beginning? The synthesis reactions, acid base, oxidation.
Yes. Those 3. Did you get it?
Solution. And then what was the last one?
Synthesis, acid base, and oxidation.
Oxidation reduction, redox.
Solution has to be solution.
Again, high application of
Hmm?
high app. Or high fever.
Yeah, that wasn't it. It's called modeling. I forgot the spelling. This is it. You just want the right amount of fluoride. If you have too much fluoride, your teeth are going to look like this.
What's so dark?
The teeth are starting to get eaten away.
Oh, the light.
Yeah. There's some talk about fluoride as well. Some people are saying that fluoride can interact with your brain and cause negative effects. But it's being debated. There's a pretty healthy debate regarding that. Some other people say no. But what you want is you want to just see all the data and then make up your own conclusions based on the data. And so there's a big push to get away from fluoride as well. So strong acid dissociates completely. Weak acids like to stay together. The fluoride doesn't want to let go. Here, the chloride's a lot bigger. They're showing them the same size. The chloride's a lot bigger. And so it's not going to have as strong of a hold on the proton, on the hydrogen. And so the hydrogen can break off a lot easier. Fluoride's a lot smaller, and it's going to have a much tighter hold on the hydrogen. And it doesn't quite let go. That's a problem with fluoride. Here are these the 7 common strong acids? Yep, those are the 7 common strong acids. It's good. Here they talk about the 7 common strong acids, and then everything else is being weak. Nitrous acid, strong or weak? Weak. And the weak acid only partially dissociates. So the major species will be HNO2. Whereas chloric acid, strong or weak? Strong. So the major species will be the ions. I think they're just doing the major species. Yeah, major species here. All right, so that's some acid base. What we're going to do is we're going to shift. There's acid base, redox, and what was the other type of reaction? Metathesis. Metathesis are favorable ion combinations. So we look at this ion combination. What's the ion combination here? Lead, 2, and then this is sodium and chloride. So we compare this ion combination. What we're going to do is we're going to swap ions. We're going to swap ions and see if we get a more favorable combination. So rather than pairing lead with nitrate, we're going to pair lead with chloride and sodium with nitrate and see if any of these are favorable. So what makes a favorable combination? What makes a favorable combination is something that will precipitate, that is an insoluble solid. All nitrate salts are soluble, and all sodium salts are soluble. So, you know, the ions are going to be distributed in solution, and they're going to have translational motion, and they're going to be kind of independent of one another. Whereas if we combine lead with chloride, chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. So this is going to be insoluble. So this is what we call a favorable ion combination. That is, if lead comes across a chloride, then it's going to form a stable lattice. And we're going to precipitate out lead-2 chloride. Sodium nitrate's not. All sodium salts are soluble. So, you know, this doesn't come together. The only way you can get sodium and nitrate to come together to precipitate is to evaporate all the water. That's the only way you're going to get the sodium nitrate to come out. But you don't have to evaporate the water for lead. You know, lead and chloride are naturally going to come together. And so this is a metathesis reaction. Metathesis reactions, we look for favorable ion combinations. And this is a particular type of metathesis reaction. This metathesis reaction is called a double replacement. We're doubly replacing the anions here in this case. And so this double replacement pattern is AB. A is lead, B is nitrate. CD, C is sodium, D is chloride. Yeah, right, ACCD. CB, sorry. Or no, AD, CB. This is metathesis, but it's a particular type of pattern of metathesis. This one is called the double replacement pattern. Double replacement. And so what we're going to do is we're going to be looking at double replacement reactions here in detail.
Can you go back?
Yeah.
Thank you.
It's a typo here. So the lead-2 nitrate is soluble salt. Nitrates are soluble, so it splits up into the ions. So these ions are separate. They don't really combine unless there's no water. And then the sodium chloride, soluble. And so what happens is the lead ions combine with the chloride. It's favorable, and will form lead-2 chloride. However, the sodium and nitrate don't do anything, but that's what's left over. And so what we're going to form is lead-2 chloride and sodium nitrate. This is what we call the ionic equation, or the total ionic equation. I call it the ionic equation for short. The other equation didn't show the species in solution like this. This is showing the major species. This is called the complete equation, or just the conventional equation. Conventional equation, we'll call it. So I'm going to call this first equation the CE. This for the conventional equation. The CE just shows you what chemicals to buy. We need to buy some lead-2 nitrate, we need to buy some sodium chloride, and we mix them together, and this is what we're going to form. The total ionic equation, I'm just going to call this the IE, the ionic equation, IE. This shows the major species. So in the lead-2 nitrate solution, the major species are going to be lead ions and nitrate. Do you expect to find any lattice left? No. And sodium chloride the same. However, lead-2 chloride is an insoluble salt, so the major species is lattice, the solid. And so this is the major species here. And then sodium nitrate is soluble, so it's just going to be this. And really, nothing happened to the sodiums. The sodiums are floating around in water. and the sodium still are floating around in water. So these are called spectators. They don't really do anything. And the nitrate was floating around in water. It's still floating around in water, which translational, vibrational, rotational motion. And so those are spectator ions. And so the next equation we have is what I'm going to call the NIE. And so the IE shows all major species. The NIE, the net ionic equation, has all the spectators removed, so nothing happened to the sodium. And so the NIE, what we do is we take a look. Nothing happened to the sodium, so essentially we just cancel those out. And then we look at the nitrates. Nothing happened to the nitrates, and so we cancel those out. If we cancel out the sodiums and the nitrates because nothing happens, then we just look at what's reacting. The lead ions combine with the chloride ions to form lead-2 chloride precipitate. And so this would be our NIE. The favorable ion combination here is the lead ions combined with the chloride ions to form lead-2 chloride. The other ions didn't have a favorable ion combination, so those are spectators. And so we don't worry about that. And so lead-2 chloride is a white precipitate, and so this would result in something that's observable. We can see here as far as observations go. This is lead-2 iodide. Iodides are insoluble too, so if we have some sodium iodide in there, that happens. It's pretty lead-2 chloride is just white. This is lead-2 chloride. Lead-2 bromide is black. And so we get the 3 precipitates there. In the precipitation reaction. So this is an example of a metathesis double replacement, and this is the full analysis where we're doing the CE, the IE, and the NIE. And so we're going to get some practice with this next time. I guess. Start with this. We're out of time for today.